Welcome to this lecture. In the last lecture, we have seen that sometimes it is very much necessary to find out the antenna's impedance. So, today we will discuss the impedance of the antenna. Now, input impedance of an antenna is defined as the impedance that is presented at the input terminals of an antenna. So, if this is an antenna, it is connected to a generator. The generator is having a voltage, peak voltage Vg, and generator impedance is Zg, that is connected to this. So, these two terminals are the input terminals of the antenna. So, here whatever we are seeing so at this point whatever we are saying that we can call as the antenna's impedance, that means the voltage to current ratio at this point, this AB terminal, that will be called the antenna's impedance. So, this is the case in the transmitting mode. Now, we can write the antenna input impedance ZA as a real part and an imaginary part. Why imaginary? We have discussed because there will be some reactive field near the antenna. So, impedance wise it will be some reactance, and obviously, we have seen that there are losses in the antenna. So, there will be some loss resistance, also it is radiation, a lot of radiation is taking place from a good antenna. So, that we can whatever radiated power that we can model as a radiation resistance. So, everything together that will give the real part of the impedance. Now, for simple antennas, the two parts, that is this array that we have earlier discussed, that will have a radiation resistance, also that will have a loss resistance. So, radiation resistance is not a loss mechanism, it is actually the radiation that is taking place. So, it is desirable, higher RR means more radiation, radiated power is taking place, and this is the loss mechanism. So, resistance due to the loss in the circuit of the antenna, that is in the conductor, in the dielectric, etc. Also the mismatch, etc., all those losses. So, these two, now for simple antennas, they can be modeled as series elements. Always it cannot be done in modern or complex antennas where you have a ground plane, where you have a lossy dielectric. Always this RR and RL cannot be put in series, but for simple antennas which we will be generally discussing in this class, if we assume that RR and RL are in series, then we can further simplify this impedance model that will go. So, now, fortunately at microwave frequencies, this loss resistance RL, this is not very high. By proper designing of antenna, we can make this loss quite low compared to RR. Now, coming back to our approach of visualizing antenna as a circuit element for calculating various values of transmitter, which may have some blocks which are analyzed by circuit approach. So, here we are assuming that the generator that is having driving the antenna, that has an impedance of Zg. So, this Zg also we can say that this Zg is also having a resistive part and a reactive part, and also Vg, it is the peak generator voltage. Peak voltage of the generator is this. Now, we can, for this whole circuit, we know that we can have a, actually you see antenna is a open and radiating thing. So, we cannot analyze this circuit because there is no load seen here. Actually, this antenna is behaving as a load to this whole circuit. So, to simplify and to come to our known things, because we want, unless until the circuit is closed, we cannot put the currents. Here actually there is displacement current going on, but to have our understanding, we can have a equivalent Thevenin equivalent circuit that I will draw now. So, the Thevenin equivalent circuit of this antenna we can draw from our whatever knowledge we have about electronic circuits, various theorems. From that we can draw like this. You see, now it looks like a thing, actually the same thing as the previous one we have done, but compared to this looks a more normal our analysis, and it is now apparent that actually our load is the radiation. So, radiation resistance is the load in this. So, now we can say that there is a current flowing through the circuit I g. Obviously, this I g is a complex quantity. So, we want to find how much power is radiated and how much power is lost in the antenna, etc., or in the circuit. So, for that we will have to find out the expression for I g. So, we know that what will be I g? I g is V g by that G g plus Z. Now, we know that for simple antennas we can write this Z I can write as R r plus R L plus J C plus. Okay. So, from here I can now write what is the magnitude of this I g, that is simply V g by G plus R r plus R L square plus X g plus X a square. Quite simple. Now we can find out what is the power radiated by antenna. So, if I call that PR, power radiated by antenna, that will be simply half I g star into I g star, that is I am writing I g mod star, mod square. Now, it is looks simple. Similarly, the other part, that what is the power lost, power dissipated at heat in the antenna, that will be half Ig square RL clear concept. So, that is the reason we always try to find the equivalent circuit. So, where is the remaining power? Obviously, the remaining power is dissipated as heat in the internal resistance of the generator. So, that we can call Pg is the power that is dissipated inside the generator, that will be again half Ig square Rg . Now, we will invoke a theorem that is well known for electronic students, that maximum power transfer theorem. So, again if we look at this diagram, this Thevenin equivalent, this is actually the Thevenin equivalent circuit. Of a transmitting antenna. So, here we can say that our objective is to maximize the power radiated. So, that means what is the maximum power that can be delivered to this radiation resistance. That will happen when we have conjugate matching. So, that means the condition for that is RR plus RL should be equal to Rg and Xa should be equal to minus Xg. So, under this scheme we can say that when this conjugate matching takes place, what is PR? It is Vg square by 8, just the same expression, you put this condition, this will come RR by RR plus RL whole square, PL as I said that usually for microwave antennas this RL is much less than RR. So, most of the power is being radiated, obviously some loss is there, and what is power dissipated in the generator? But here again under this condition I can say I can cut this and cut this. So, it is Vg square by 8, or let me write Vg square by 8 RR plus RL. So, under conjugate matching we can say that Pg is equal to PR plus PL. So, also we can find out the maximum power supplied by the generator. How much power is power supplied by the generator is half Vg Ig star. So, it is half Vg star by 2 RR plus RL, 2 coming because of conjugate matching. So, that is coming as V g square by 4 R r plus R L. So, you see that whatever total power is supplied by the generator, only half of that under conjugate matching can be radiated and half gets dissipated in the internal resistance of the generator and the remaining half power goes to antenna. Now, if we can make antenna lossless, that is conductor and dielectric loss to 0, then that amount of power also will get radiated. So, that is why we always try to do, try to use the very good conductor, like that is why if you want very good or very small loss, then you can have gold or silver. Actually, silver is the best one, but silver cannot be machined easily. So, gold, and you can use gold for making antenna, or you can use copper for making antenna, and also the dielectric, those are very low loss dielectrics are used. So, that this R L factor is very small. Also, we assume that the impedance matching is there between the antenna and the interconnecting transmission line, because here when we are saying that connecting these, here we have not explicitly shown, but obviously the generator cannot directly connect to the antenna. So, there will be a transmission line. We are assuming that that transmission line we are having an impedance match. If not, then some amount of more power will be lost. If matched, then the whatever power is supplied Vs, the Ps, that can come to the half of that can be delivered to the antenna. So, you see the usefulness of antenna's impedance. That is why any antenna we generally try to find what is the impedance, and we have seen that people generally demand that the for antennas, nowadays modern antennas, people say that the reflection loss should not be more than 10 dB. So, that is why that means 1/10 of the power can be made to loss. So, it is an 10 dB impedance bandwidth is a useful parameter for an antenna. Now, what will happen in the receiving mode? So, let us draw the receiving mode, because that one we have seen in the transmitting mode. In the receiving mode, we have that antenna. Now, in this case, the wave is coming. Okay. These are the incident wave from some distant source. This is coming. The antenna is receiving. Then, through a transmission line, the antenna will be connected to some load. That load may be a spectrum analyzer, may be a receiver, anything, but let us say so. Let us call that load as, because Z L will be getting confused. So, Z T let us call. Okay. So, if we, this is the load, let me call this is a load. Now, what will be the Thevenin equivalent of this? Achha, I have not marked A B. Now, let us draw the Thevenin equivalent. So, this side A B, this side I can easily draw that Z T will be some real part. So, R T and some A part, reactive part X T. Okay. And this antenna I know how to model. So, there will be a lossy part R L, capital L, R L, then there will be a induced voltage on the antenna, because this incident wave is coming. So, at these antennas, if you say output terminal, there will be a voltage induced because of this field. There will be an electric field between 2 points. So, there will be a voltage, let me call it Vt, and then there will be that radiation resistance of the antenna, and then this reactive part of the impedance, that near field effect, etc. So, this is the Thevenin equivalent. I can say that this is the Thevenin equivalent circuit of the antenna, and obviously now there will be a current flowing IT. So, what is IT now? I can very easily write IT is Vt, the induced voltage, divided by Rr plus RL plus RT plus J XA plus X plus XT. Okay. So, now from here similarly we can find out how much power will come, etc. How much power RR will dissipate, how much A, etc. Now, the input impedance of an antenna, so we have seen it. Now, it is generally a function of frequency, because all these things that at different frequency, the reactive part, etc., that will change. So, it is a function of frequency, and antenna is matched to the interconnection transmission line. When we say that, suppose this antenna, as I said, that there will be a transmission line here to connect it, that transmission line has a characteristic impedance. So, we are assuming it is matched, but characteristic impedance is a real quantity, and over a narrow frequency band only it will be matched. At other frequencies there will be a mismatch. So, that needs to be taken into account. So, I can say that the input impedance of an antenna depends on several things. On what? First, obviously, it is dependent on frequency of operation. At different frequencies, obviously impedances, etc., they are different. Then it depends on geometry of the antenna, because it is an antenna. So, when we are saying radiation resistance, that depends on the geometry, as we have seen, that radiation resistance of a current element, etc. And later also we will see that better and better antenna means better your radiation efficiency. So, that means your RR will change. So, obviously, input impedance depends on geometry of the antenna. Then also the method of excitation of the antenna, because for high frequency things, how you excite the antenna, how you put this transmission line, how it is connected to the antenna. There are various ways of connecting, loop coupling, probe coupling, etc., and that will change the impedance. That will drastically may change the impedance. If the excitation is not proper, you won't get the proper coupling, etc. So, input impedance definitely depend on method of excitation. Then here one thing we are not saying, that we are assuming that near the antenna there is no other structure, but in reality any conductor, any structure, even a dielectric structure nearby, that will affect, because antenna is radiating a field, that electromagnetic field will go there, then that there will be some secondary currents induced in those bodies, and that will again irradiate and that will come here. The net effect of that is a mutual coupling. So, a mutual impedance. So, that means input impedance, whatever we have discussed here, that was the total effect, that means self impedance plus mutual impedance. So, that mutual impedance will get affected the moment I have a nearby thing. The thing is in the low frequency or in the circuit theory, generally we do not have this impedance of certain thing is not dependent on someone else. But you have seen when we have two coils, then they are nearby, so there are mutual things. Now, actually there are, though that is a low frequency case, but there is a magnetic coupling, but here you see electromagnetic coupling is also there. So, any conductor dielectric nearby that will affect the antenna, that will give a mutual impedance, and that will affect the total impedance. That is why I can say that proximity to surrounding objects. Nearby, okay, surrounding means then any other thing, also obviously the material of the antenna, because all those laws etc. depends on what material we are using for the antenna. So, you see input impedance, though we are giving here certain values, but we should remember that all these things affect this input impedance. So, we have seen how to model, you see even in circuit theory we can have this antenna model. So, that is a nice way that we have started the current element from the analysis from field theory. Once we have known that, field theory gives us all the informations, and from that if required, when we are connecting the antenna with a transmitter or when we are connecting the antenna with a receiver or load, we can model the antenna as an circuit theory object. So, we can find a more impedance for that. We have seen the moment we have found that, we can find the Thevenin equivalent, then we can apply maximum power transfer and we can find out what is the condition for maximum power transfer, and by that we can have what is the power dissipated in the antenna etc., or how much power the antenna is putting to the load. All those things we can calculate in our usual way. So, input impedance is a very important parameter. We will see that this impedance, actually the narrow band antennas, for them if we know the impedance and if we can make the reactive part of the antenna at a particular frequency 0, then that antenna can be called as a resonating antenna. Actually, that is the practice in dipole etc. we will see next when we will go to those things. Our job is to make that, if we can somehow cancel that reactive part, then we can say that antenna whatever we are giving, it is resonating. That means, it is putting the whole thing into the as a radiation is taking place and there is no reactive storage of energy. All the energy that is given, provided there is some loss, but other energy is that time we say that antenna is resonating. So, resonant antenna is the normally narrow band antennas. At wide band antennas we cannot make resonant, for them we design is non-resonant, but this antenna impedance is a good way of seeing what is happening to the antenna, how much it is radiating, how much it is losing, and also for other elements, the generator or the receiver, it gives us that how much power I can take, how much power I can give etc. Okay. Thank you.